So we know that the semiconductor, there's a history for the semiconductor. When you start with the, for example, the old sets, electric sets like this, old sets that has these tubes. After that, they invented the transistor and diode, and then after that, these transistors and diodes are embedded into ICs, integrated circuits. And then after that, these integrated circuits become large scale ICs. This is what you see, for example, in your motherboard in the computer. You have a chip that has I don't know how many electronic components, for example. So this is the IC. So this is a history of semiconductors. And you see here when you have start, for example, having this transistor radio. I don't know. Of course, you did not see this stuff, and this clock, for example. And now we have the smartphones and laptops. And for example, I remember when I used a computer for the first time. It was, I believe, it was the hard disk. Sometimes I remember I use a computer that does not have a hard disk, so we use a disk, floppy disk, called floppy disk. And the memory, I can't remember what was the memory at that time, but I remember, for example, yes, I believe the memory was something in mega, 4 mega, 8 mega, something like this. So why? Because there was no chip that has this large scale memory. This slide here is just you need to look at it in your computer because it is very hard to see it in the PowerPoint. But it shows applications per year. For example, starting from 1086, for example, until 2017. Starting from this all devices until the time we have right now. So this slide is just a variable. So we know all this stuff, but just a review here. In this book, this is what they are using. They use R as a resistor, okay, and this is for DC or actual circuit component DC. When they use little r, small r, this is a AC equivalent, okay, and if you have a capacitor, it is C. The inductor is L. They use capital Q for the transistor, call it bipolar, or FET, FET, and the diode D. The voltage, if it is DC voltage, it is capital V. If it is a small v, so it is AC. If it is a current, for example, if it is capital, then it is DC. If it is a small, then it is AC. And all of them, you can see that all of them are italic. So these are the symbols that are used in this book. Maybe, of course, they are different in other book. So let's start here. This is real start. Everything starts with atomic structure. We know we know the structure of the atom. It has protons, it has neutrons and electrons. The protons have the positive charges. The neutrons they don't have charge; they are neutral. And we have electrons, which have the negative charge. So these are the electrons, okay. And you have here you have the protons and the neutrons. Okay, so when you look at it like this, of course, this is not the reality. The reality is what? Let's see. Let's see these points here. So the atom mass is mostly in the proton and neutron. So the mass is generally here. The electrons, you can say that they have negligible mass. See here, the mass for protons, for example, is 1.67 10 to the power of negative 14 gram. But for electrons are 2,000 times less, 2,000 times smaller in mass. So you can neglect them. Also, the radius of the proton radius is 0.87 times 10 to the power of negative 15. Okay, the distance between to the nearest electron, so the distance from here to here, the radius is this radius here. This is the radius. When you compare the proton radius, you see this one, and this distance is almost what? Let us forget about this number here, okay? But 10 to the power of negative 11 and 10 to the power of negative 15, So this means that it is 10 to the power of 4 times. So it is 10,000 times, for example, roughly, it's 10,000 times. So the distance between this protons here and the first electron is 10,000 times the size of what of the proton here. So they are all very far away. We are very far away from the nucleus. Okay, so imagine that you have something like this here, and it is 10,000 times away from it, which means that what that the atom is almost empty, almost empty. So it has a point that has the protons and neutrons, and then after that, at a very far, big distance, you have the electrons. So even this solid material like iron, for example, it is the same. It is the atom is almost empty. So this is imagine that all these atoms are almost empty, nothing inside. So here, let us see this explained here. So electron is 60,000 times away from proton than proton size. Okay, of course, when you use the right number here, 5.3 and 0.87, so it is 60,000 times. Okay, so imagine this is look like what? Like imagine that you have a golf ball with respect to a sphere that is around 0.75 miles. So imagine that you have a ball like this, small ball, and this is in the sphere that it is 0.75 miles, 3/4 mile. Okay, this is atom. How the atom look like? And see here, there is no big difference between gas, for example, like hydrogen, and tough material like diamond, for example. They are all empty, all empty. This is the reality. But what happened here? Why this material is solid and why is this just a gas? This is because of the interaction between the atoms. That's it. The interaction between the atoms. When you try to, of course, try to imagine the atom, how the atom look like, there are many models to imagine how the atom look like. So, for example, this is what we call it here, planetary model. So this look like this. We have this in NASA, but this is not right. This one is not correct, of course, but it is a just symbol, and we try to imagine how it look like, but how the electrons are moving around the nucleus. So try to imagine how it looks like, but this is just a model, so it's helpful for imagining. So the atom components are smaller than shortest wavelengths of light. Okay, so we need to make a model to explain its behavior. So this one here, this model, is the most famous model, and this is a planet around the sun, like a planet around the sun. And remember again, this model is incorrect, is not accurate, but it is just a model. The electron inhabits a region of 3D space. So what in reality, the electrons around the nucleus, they have a 3D space. So they are moving like this, for example. They are actually inhabit a shell around the nucleus. So it doesn't move in a plane like this, like what we have here. So we can't precisely plot the position and the trajectory of a given electron. So we tried to imagine that we have a shell. In this shell, the electron is moving around the nucleus. So here, the best way is to make a plot of where the electron is likely to be. And this is what we call it here, a contour. As a contour look like this sphere here, sphere. So how we do that? We record the position. We have electron. The electron is moving around the nucleus. So we try to record its position, and then we plot, track these positions. Okay, and this plot will look like a cloud of dots around the nucleus, like this shell here, or this sphere. So this cloud is referred to as what? As orbit or shell. So you see, that's why we have this orbit or shell. Orbit or shell. And each shell has some subshells. Each shell has some subshell. So how it works, this slide here is a little bit complicated, because if you have, for example, have a shell, this shell has each shell has a number. So we have shell number 1, shell number 2, shell number 3, 4, and this depending on what we call it here, the principal quantum, or the energy, amount of energy in the shell. So when you have a higher number, we have a higher energy. So shell number 1 is lower than shell number 2, lower than shell number 3, and so on. Okay, but each shell has also subshells. Okay, for example, each shell has subshells, like we call it S, P, D, F, and so on. S, P, D, F. Okay, so for example, shell number 1 contains subshell S, so it has only S. So since it is 1, we call it 1S. 1S. Okay, only. Shell number 2 will have 2 subshells. So it will have S and B and P. So we call it 2 because it's shell number 2, and 2S and 2P. So it has 2S and 2P. And shell number 3 will have 3 subshells. So it will have 3S, 3P, 3D. So 3, this is a shell number. So that's why I call it 3S. Just differentiate between 1S, 2S, 3S. So 1S is a subshell S for shell number 1. 2S is a subshell S for shell number 2, and so on. So now if we have shell number 4, for example, it will have what? 4S, 4P, 4D, and 4F, and so on, and so on. Okay, and each subshell, okay, has number of let us call it here, they are parts. For example, shell number S has only 1. Shell number P, subshell number P can have 3. Shell number D have 5. Shell number F have 7, and so on. Okay, so it's a little bit complicated, as I said. So again, here subshell may have one variation on S, only one variation on S, so to have only one S. Okay, but 3 variations on B. So for example, here if you look at shell number 2 here, so it has one variation for S, so only 2S, but 2P has 3 variations, so we have 2S1, 2P1, 2P2, 2P3. And for shell number 3, this one has only one variation, so it has only 3S. This one has 3P1, 3P2, 3P3. And then this one has 3D will have 5. So it will be 3D1, 2, 3, 4, 5, and so on. Okay, so the subshell may have one variation on S, 3 variations on P, 5 variations on D, 7 variations on F, and so on. So shell number 2, and each variation can contain 2 electrons. Each variation can contain 2 electrons. So for example, shell number 1 contains 2 electrons in 2S. So this one has 2 electrons. 2 electrons. So let us see here. So this one here, each variation has 2. So this one can have up to 2 electrons. Okay, what about this one? This one can have 2. Okay, and P has 3. 1, 2, 3. Each one can have 2 electrons. 2, 2, 2. Then the total is what? Is 1, 2, 3, and 4. 4 times 2 is 8. So this one can have 8. Okay, what about the third one? This one has only one variation, so can have 2 electrons. This one has 3. 1, 2, 3. Okay, and this one has 5. 1, 2, 3, 4, 5. Okay, so let's add them. 2 here, 2 in this one. Okay, and 2, 2, 2. Then it is 8, and then 2, 2, 2, 2, 2, 5, 2. Then it's 10. 10 plus 8 is 18. Is 18, and so on. Okay, so this is you can tell how many electrons in each shell. Okay, so shell number 2 can contain up to 8, as I explained. Why? Because it has 2 in shell 2s, the subshell 2s, and 2 in each of the 3, okay, 2p variations, as I said here. So you see, you have 3. So each one has 2. Then the total is 8. Okay, let's see shell number 3 can contain up to 18. How? Because it has 2 in 3s and 2 in each of the 3 of 3p. Okay, 2 in each of them. That is 6. 6 plus 2 is 8. And then 2 in each of the fifth or the 5 3d. Then in this case, you have 5 times 2 is 10. 10 plus 8 is 18. What about shell number 4, for example? So shell number 4 will have how many? We have 4s, 4s, okay, and what? And 3p and 4p, okay, and what? And 4d and 4f. Okay, so now let us count how many electrons in this one here. This one here has only 2, so this is 2. So let's add 2 here, plus 4p has 3 variations. Each one has 2. That is 6. So plus 6. Plus next one, 4d has 5 variations. Each one has 2. So it will be 10. Plus this one has 7 variations. So each one has 2. Then it is 14. Okay. Then 2 plus 6 plus 10 plus this is 18 plus 14 is 32. So this one is 32. So this is a number of electrons in shell number 4. And there's a relation that to make it easy for us, that is 2n square. So if n is a shell number, if n is 1, then it is 2 times 1 square, which is 2. If n is 2, then it is 2 times 2 square, which is 4 times 2 is 8. If n is 3, will be 2 times 3 square, which is 18. And then if n is 4, will be 2 times 4 square, which is 32. Okay. The next slide can make it, can simplify it, and we'll see it in figure to look better. So if you don't understand this slide, let us see the next slide. So here is the energy level. So here we are going up. This is the energy level. Look like this. Okay. So if n is number 1, is shell number 1, you have only s. You have only s. Shell number 2, you have s and p. And you see p has 3 variations. Okay. Shell number 3 has s, has 3 variation for p, has 5 variation for d. Okay. And in number 4, shell has s, 1 variation for s, 3 variation for p, 5 variation for d, and 7 variation for f. And so on. So if you, for example, have n equal 5, n equal 5, then as I said before, the number of electrons is 2 times n square. So if n is equal 5, n square will be 25, then 2 times 25 is 50. So you have up to 50 electrons. So of course this means that you have 25 variations here. So you have 2 variations for s, and you have 3 variations for p. You have 3 here, p, p, p. The same like this. Oh, come on. And 5 variation for D, the same like this, and 7 variation for F. And then you have 9 variation for the next one. 9 for after that A, B, whatever, S, P, D, F. Then you have, I don't know what's the next one, and so on. Okay. Also, you can see it here. This is so you have the nucleus here somewhere, and then you have the shells around the nucleus. So I'm talking about this figure now. Okay, so for n number 1, so let's use the laser. So in the number 1, you have 2 electrons. This 2 n square. So why? Because you have one variation S, and for n number 2, you have one variation for S, 3 variation for P. For n number 3, you have one variation for S, 3 variation for P, 5 variation for D. Or for n number 4, you have one variation for S, 3 variation for P, 5 variation for D, 7 variation for F, and so on. And each variation can have up to 2 electrons. Okay. So each subshell can have 2 electrons. As I said, each subshell variation is supposed to be variation, can have 2 electrons. So each one of these poles here can have 2 electrons. So when we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Each one will have 2. Then the maximum is 32. Okay, so this is how you count the number of electrons in each shell.